Hi folks, today we're going to discuss the article entitled Adversarial Examples, Attacks and Defenses for Deep Learning by Si-Young Pan He, Quil Zhu, and Xiaolin Li. This is an article published in June of 2018 and has been cited over 1,497 times. To begin to understand attacks and defenses for deep learning, it is first necessary to understand the concept of a decision boundary. A decision boundary is defined as the region of a problem space in which the output label of a classifier is ambiguous. Let me provide an example. Imagine that you have a duck-rabbit illustration, otherwise known as a Jastrow diagram, and that when you start manipulating this diagram, you can move it from looking like a rabbit to looking like a duck. And you can basically graph this movement in a 2D space such that on one side of the graph you have rabbit, and the other side of the graph you have duck. Now you'll notice that at one point it's somewhat ambiguous whether or not the illustration is a rabbit or a duck. Namely, you can't decide. At this point, this is the decision boundary, because on one side of this boundary you have the class of rabbits is illustrated. On the other side, you have the class of ducks. So similar to how we would struggle with determining whether or not something is a rabbit or a duck, deep learning solutions also have to struggle with such ambiguities. Okay, so how do deep learning solutions deal with the ambiguity of decision boundaries? Well, let's take the following example. Imagine you have a test set X in the form of a duck image, and you pass this image through a neural network, and a classification decision is made in the form of Y. The decision being that it's a 51% chance that the image is of a duck and a 49% chance that the image is of a rabbit. Let's make some observations from this classification decision. First, this neural network is particularly weak in identifying a duck versus a rabbit. Next, the decision boundary between duck and rabbit is ambiguous, and that the neural network can be easily confused between the two. And this creates a few issues. Namely, that bad actors can exploit this weakness in classifying as part of an attack, and that this weakness is compounded in the multi-class neural network setting, namely where we have a neural network that is rendering a classification decision not regarding just two classes, but rather multiple classes. Let's look at an example attack in a multi-class neural network. Consider, for example, GooglyNet. GooglyNet is a publicly accessible deep learning model trained to classify over 1,000 objects. These objects include animals, pencils, keyboards, and other things. Now imagine that you pass in an image of a panda, and GooglyNet tells you that there's a 57.7% chance that the image is of a panda. Further, imagine that you pass in a portion of an 8-bit image encoding, and GooglyNet tells you that there's an 8.2% chance that the portion of the image encoding is a nematode or a worm. Now, if you combine the two and pass those into GooglyNet, GooglyNet tells you that the combined image is of a gibbon and that there's a 99.3% chance that it is in fact a gibbon. More on this attack. First, this is what's known as a black box attack, because the attacker only knows the inputs and outputs to the neural network and doesn't actually know anything about the actual trained model itself or how it's architected. Further, this is an attack on a publicly accessible neural network. Another example of a publicly accessible neural network is ChatGPT. Further, this is an attack that exploits a weakness in GooglyNet's ability to classify panda images. Further, this is a non-targeted attack in that the attacker didn't seek to facilitate a particular outcome. We'll talk about targeted attacks in the next slide. Finally, this type of attack shows that small perturbations are best, namely those that are imperceptible to humans. So for example, here, a very small portion of an 8-bit encoding was used to facilitate the attack. Let's talk about some flavors of targeted attacks. The first is a false positive attack. This is an attack where the goal is to intentionally generate a negative sample, which is misclassified as a positive one. Another type of attack is a false negative attack, where the goal is to intentionally generate a positive sample, which is misclassified as a negative one. A final type of targeted attack is just a targeted attack that intentionally generates a sample that misguides a neural network to a specific class. So for example, passing in a panda image where the result then is classified as a gibbon. The risks of these type of attacks come in the form of being able to mislead facial recognition software, fingerprint recognition software, or any application that uses AI/ML as part of its security regime. While the article discloses a number of methods to create an adversarial example, we're going to focus on a generative adversarial network that is used to create an adversarial example. A GAN is comprised of two supervised learning models. The first is a discriminator that determines the probability of y given an x, and the second supervised model is a generator that determines the probability of x given a y. Used together, the goal of this GAN is to create a generator that consistently force a false positive or false negative decision by the discriminator. In terms of steps of how this works, basically the discriminator is trained to classify relatively well, and once trained, it's frozen. And then the generator is fed noise and then an approximate distribution of x values that are then used to create an adversarial example. Once a discriminator can be convinced that the adversarial example is real, hence the attack being successful, then it is unfrozen and then retrained, and then you repeat the process. Critical to understanding a GAN is the concept of the cost function. The cost function is a function that is passed the training set in the form of x and a classification decision in the form of y, and then it basically makes a determination of the plausibility of x for a given y, and then uses this determination to create what's called a theta parameter, which is the likely distribution of x in a particular space. What's interesting about the cost function is that it then passes this theta value to the generator, such that the generator actually never sees the actual x data or image itself. Notwithstanding the fact that it can't see this image, the theta parameter is optimized by the generator such that random noise is upsampled and mapped to the distribution of the x values. And then as this mapping distance becomes smaller, better and better adversarial examples are provided to the discriminator. Hence, really, the generator is basically passed noise and then the theta parameter, and it attempts to then upsample or modify this noise to the theta parameter. So how do you use a trained generative adversarial network? Once the generator is sufficiently trained, you can use it as an unsupervised model to create adversarial examples by merely passing in noise. Some applications of this trained generator are that it can be used in adversarial attacks, which is a bad use. It can be used basically to create deep fakes, another bad use. It can, however, be used to basically create artwork through the concept known as style transfers, a good use. Finally, it can be used to create synthetic data, which is a good use. So instead of having to get data from persons and deal with privacy regimes around persons, for example, you can just basically create synthetic person data. This begs the question, though, of what type of AI/ML models can this trained generator be used on? To answer this question, we have to understand and explore the concept of adverse sample transferability. So what is adverse sample transferability? Adverse sample transferability is a concept that adversarial examples that affect one model often affect other models, even if the two models have different architectures or are trained using different training sets, so long as both models are trained to perform the same tasks. Let's take an example. So imagine you have a learning substitute model, for example, a generator for a duck-rabbit classification problem, and you use that to conduct a targeted attack against any AI/ML model used to classify an image as a duck or a rabbit. Key points here are really that the classification task, for example, facial recognition, is dispositive of whether the adversarial model will work in a targeted attack. Next, the same learning substitute model can be used for any classifier irrespective of AI/ML type, neural networks, decision trees, etc. And finally, no access to the training data of the classifier model is required to mount an attack. So why does adverse sample transferability work? Learning substitute models, for example, a generator approximating the decision boundaries of targeted classifiers, alleviate the need of previous attacks for knowledge of the targeted architecture and parameters, which is another way of saying, irrespective of classifier type, classifiers trained to solve similar classification tasks, for example, facial recognition, will have similar decision boundaries. And weaknesses in these decision boundaries may be exploited by a learning substitute model trained to create adversarial examples for the specific classification task. Now, what are some defenses for deep learning? One is network distillation, which is really the concept that if you reduce the number of ambiguities in the network will be less prone to be susceptible to an attack. Another is adversarial retraining, which is really the idea that you can train on the adversarial examples to make a network that won't be susceptible basically to adversarial examples. A further is adversarial detecting, which is really that you add a detection filter that decreases the ability to identify a decision boundary by an attacker. And finally, another concept that can be used to defend a deep learning network is input reconstruction, which is really the idea that you get rid of the noise that's a part of the adversarial example to then identify the original input. Summing it up, decision boundaries are common to most AI/ML models. Ambiguous boundaries can be exploited via adversarial examples. Generative adversarial networks are one type of method that can be used to generate adversarial examples. Adverse sample transferability dictates that adverse examples can be used against any classifier that attempt to solve common classification problems, irrespective of the type and training of data. I hope you've enjoyed this presentation.